Alright, so this has a huge delay compared to Twitch. But yeah, we're just gonna plod along here for a little bit. I'm gonna see if I can't get a preview of this from my actual channel page. Maybe. My channel. I'm live now. Hey, that's like. Alright, I'm just gonna preview my audio for a little bit again, make sure it's working alright. Alright, I'm just gonna preview my audio for a little bit again, make sure it's working alright. Audio level's alright. Yeah, I mean, that's about as loud as it's gonna get until I start eating this microphone. That looks better. Now we're just touching into the yellow. Yeah, I mean, that's about as loud as it's gonna get until I start eating this microphone. That looks better. Now we're just touching into the yellow. There's not too much echo. There's not too much echo. There we go. That sounds pretty good. There we go. That sounds pretty good. Just getting set up to just oh wait, where am I still coming from? Okay. Just setting up some LinkedIn posts for this. Okay, well, let's get to some actual development, shall we? I'm just gonna keep drinking beer and rambling on as I bumble around shifting between data sheets for the @megas I2C functionality and my Ubuntu virtual machine where I'm actually doing the development. But having made that statement about the beer, I'm out. So I'm gonna put a BRB screen up right quick and take a quick break now that I've got the stream actually working and it sounds like it's doing all right. And then we'll get back to working on some more I2C development. Okay, so where I'm at so far is I have this old set of libraries I've written for doing some robotic stuff on AVR microcontrollers. Oh boy, it's after midnight, isn't it? Oh, yeah. But I didn't have any of the slave mode features implemented, and all the stuff that relied on interrupt functionality wasn't implemented yet. Everything that I did have implemented only worked via blocking reads and writes as a master. So in that library, in that class, I had started to add in some of the slave stuff, but then realized some of the stuff that was already there wouldn't quite fit. So I kind of pulled the trigger on starting over from scratch. So yeah, so we've got so we've got this AVR I2C class. It's got a couple defines at the top, a bunch of function pointers that we'll get to in a second. My trackball needs cleaning. But here's our class. I was originally going to write this so that you could pass in which registers and bits were needed for specific operations. However, in looking up the documentation for just about most AVR chips, they all only have a single I2C bus. So I'm setting this up to only support one bus. If this ever needs to get ported to a different platform, we can maybe revisit that. But this will set up a predefined I2C object instance. So just like in the Arduino platform, there's always like a serial instance that's predefined for you. This will have an I2C instance predefined for you. And then it's up to you to initialize master mode or initialize one of the slave modes, or you can do init master and init one of the slave modes before you call begin. And at that point you can do master or slave or mix mode master and slave. Whew. I don't think I've ever tried starting a stream at midnight before. I kind of just wanted to test YouTube streaming. It was giving me some trouble at first, but that turned out to be my audio software on my computer that I use to mix together and monitor, even though I don't have that many dedicated hardware devices. But yeah, so I've got pretty much everything defined. Oh god. This is gonna happen. I'm probably just gonna shut the stream down if I can't stop yawning. But I've got the header file defined, and I'm starting on most of the actual implementation stuff. So what I'm working on right now is getting the master mode read and writes back up and running, similar to what was in the old files, except unlike the old files, they're always going to operate asynchronously. So, for instance, with a write, and we're going to look at the register mode. There is some raw modes as well. You see the only difference between these method overrides that ones have a register number to write to, these ones don't. So these raw modes just spit data out on the bus without conforming to the register, what would be the word, paradigm. But there's a common way of addressing specific bits of data that you're reading or writing with most I2C devices. But if you were just doing something like spitting data out to an LCD display, you'd probably want raw mode, or maybe you want to handle how registers work a little bit differently in your application, so you could use the raw mode instead of the register-based modes. But we'll be focusing on the register-based modes because I'm initially going to test this out with a BNO 055 IMU that I have that connects via I2C. That's all, make sure this is all working. And then eventually this AVR that I'm running this code for will just become a motor driver controller that will then interact with the Raspberry Pi over I2C. Browser to save some data. Okay. So yeah, so the way this works is you can either do, for the register write modes, there's a single byte write and a multi-byte write. So in the multi-byte write, you can pass in a uint8 array, which would just be a pointer to the first element in the array and how many elements there are. And it'll store the address that gets set. And the reason why we need to store these to class instances is because we're not actually doing anything with the bus in this immediate call other than requesting access to the bus as a master. And then it's going to call an interrupt function up here once that starts. So if we successfully get access to the bus, it would call this interrupted vector, which we're then passing to a method within the class so we can modify the class variables. Which means I should actually change some of that stuff to volatile. We'll have to take a look at that. But then we'll read out what the two-wire interface status is, and if we successfully get access to the bus, it will be this case. Then we'll check if we're in register mode or not. If we're in register mode, we'll write the register address out to the bus first, and then once that, and we'll mark that we no longer need to write a register, at which point it'll start sending the data out. And one of the tricks I'm doing is if we're doing a single byte write, we're storing that value into our own local value variable, and then we're sending that one element, we're turning that effectively into a one element array that can get used by the write n function, so we don't have to have a whole bunch of duplicate writing code. We basically get to adjust things just a little bit so that we can reuse our normal register write mode. So yeah, so that's the start of it. Once we get to the start, so some things we're going to need to mark as volatile is this entity we're going to use in there. That's going to be our slave address, whether we're in read or write mode. So that's something else I need to set that I didn't set. Oh. And we're going to do read equals false. I don't know if that needs to be volatile. Probably does. Take a look at my circular buffer. That was volatile. But none of it was, and that works. So you know what, we'll go back to most of this and not volatile. And we'll go through and we'll start adding volatiles in if we start noticing problems. So once we get to start, we're going to want to check if we're in write or read mode. So if read or we're in write mode. Actually no, the first thing, because if we're in write or read mode, that doesn't matter until we start sending or receiving data. But if we're in register mode, even if we're in read mode, we're first going to write the register value. So that is going to be first thing we're going to do now that we're handling this is set that to false. And we're going to load into the data register the register value. So that's in our write n method. Store the register that we're going to write to there. Oh wait, no. No. We're not to the data yet. We have to do the address. So this is going to be WDR equals slave address shifted left 1 merged with read do we? Address packet format. Here we go. Okay, so if the read write bit is set, a read operation is to be performed. So if it's read, that's set. If it's not read, it's unset. So we'll load into the data register the address we're going to we need to check to see if we need to ACK or not. Well, actually, in this one, we're always going to. Well, no. Wait a minute. We're not always going to ACK. When we're doing the slave address, it's the other side it's going to be ACKing or not. Somewhere we've got these tables. So like master transmitter mode, start condition, yeah, the enable ACK doesn't matter because we're reading the ACK from the other side. So we'll say next false. So we'll do the master read at first because that's going to be the first function we check out. The IMU has some registers that report the device IDs and some version numbers. And we'll make sure we're reading those out. So master receive slave ACK. So this is going to be at this point we need to send the data, and this is where we're going to look to see if we need to send the register first. The other thing we need to do, well, no, in this case, we're always going to send the ACK. So once we're in the data phase of this operation, as long as we want the slave to keep expecting bytes from us, we will send an ACK. And then once we are going to tell it that the next byte, that's right, so the ACK or NACK is whether the next byte is the last or not. So that's going to be data n is greater than 1. So if it's greater than 1, if we've got 2 bytes of data to send, the next byte isn't the last one. Oh, and now it's raining outside. Nice. If the next byte, if there's only 1 byte of data to send, then the next byte will be the last byte. So we NACK it now, and then on the next byte, So then on the next byte, the local AVR chip knows to respond with a NAC to say, okay, we're done receiving data. We're going to be releasing the bus. So this next and this ACK isn't setting it for the byte we're currently sending. We're sending this byte, and then this ACK value is telling the AVR chip, the I2C module, how to respond to the next byte that's received. So if we're not in register mode, we're going to go right into data mode, where we're going to want some more private methods. Void. Do we want to send register? I think we're going to want to send register method. This is going to look the same in pretty much any of the register mode. So send void send data. In here, void see. We don't need to pass any methods into here because these all already exist in the class members. So if we're sending the register, we're going to send the register, we send the register. Otherwise, we send data. This is going to be data register equals data. So we're going to dereference the current data pointer, data buffer pointer. We're going to do data if n is greater than 1. If data 0, we're going to a data pointer next if data n is greater than 1. We're gonna need doing all the right methods first. Even though the first thing we're going to be testing is read data. So pointer data equals basically just going to be the opposite of Send data. I may move this comparison into our next method. But we'll give this a shot. Let's see if this compiles. Does. In our write method. What do you mean that's unused? It's used right here. Or is it because we never read it? No, because I've got busy. In constructor. Oh, yeah. Derp. State. State is going to be idle. Status. Last interrupts status register. So that's going to start off at 0. That's what I got messed up. Okay, so now it should stop complaining about that. We just got some unfinished methods so far. We can go ahead and get this set up. So we're gonna start this off. You know, we're just gonna say master read, even though initially we're gonna do one cycle of master transmit. This is going to ultimately be a master read. So these are very, very similar. Just the differences between them. Now, so that's a good point, is after we send the start bit, is we need to see if our read bit is, so we need to set the read bit if we're read and not master register, because for master register we need to start off on a transmit, so we need to start off on a write. So I'm going to start off by checking if we're registered. Not where, so let me undo. Oh. Want this, so if register, so it's good I did this because it reminded me that that's what the variable is. So if we're in master register mode, we're going to write the address and not set the read bit. We're going to leave it as 0 because we need to write the register to it first. So this is where this is where we get master transmitter slave ACK. We're going to want to see if we're in read mode, at which point we're going to need to well, we're going to need to write the master register no matter what. We're not gonna unset master register just yet because we're gonna wait till we get the data ACK. That's because we're gonna still check it one last time. So if we were master register and we're read, that's when we're gonna send a repeated start and switch over to master receive mode. Actually, no, we don't need to check that one because we can unset master register. Now we'll no longer need to send it. We're going to check read. So going to load into the data register is register. So whether we're reading or writing. Do both directions have that use of the enable ACK? You know, like no point master transmitter. There, it's only the read. So in master transmit, we can always just say false. Then in data ACK, switch to read mode. We're going to send a repeated start. think. Master transmit. Receive an ACK. And if we write the start bit again, repeated start will be transmitted, at which point we can then resend the address, change to read mode, so we will set the read bit. So when we get a repeated start, we're going to do if I don't need to do any conditionals here, because this is only going to happen in between switching between master transmitter to master read. So let's set, write the address, left one, now this should always evaluate to 1, because the only time we should get into the repeated start is if we're reading. But whatever. We'll leave it as this for now. Now this is going to be, we're going to look for the, oh, I didn't finish copying all these descriptions over. So that one. That's right, I was in the middle of doing this when my old skydiving buddy called me. Got a little sidetracked. And then by the time that phone call was done, I realized that YouTube had approved me for doing live streaming. So then I started playing with that. And now I gotta get caught up on all the stuff that I'd started but hadn't finished. That's this one. So this actually counts as 2. Read or write or read. I mean, really, it's always if arbitration is lost. Doesn't matter what mode it's in. I don't know why they have 2 different codes here that are both defined with the same value. Transmitted, ACK received, SLAR and NAC. ACK. SLAR. Now we're in the slave mode. Some of these descriptions will match some of the descriptions from the master mode. It's just that somebody else has requested data from us instead of us initiating a data transfer to somebody else. Okay. Got the start. So we're going to initialize in master transmit. Transmit. So data app. Okay, so this is change to master read by initiating so basically after a start or a repeated start is when you can send the slave address, and in the slave address byte is also included the 1 bit that says whether you read or write. Doing a start is always what is needed to change whether you're in receive or transmit mode. However, after we're already active and we do a start again, it's going to be a repeated start. That's when we're going to readdress the slave. At that point, it should be SLA-R. So now it should be down master read slave act. So if we still, well, when we are in master read slave act, we should never need to send the register. By the time we get into this state, we're already ready to read data. And also send data is not even the right method. Good lord. We're going to read data. Well, after we do a master read slave act, we're not going to read data. We're just going to do next. And then in the master read data act, this act return confuses master receive mode. This is code 5058. So this is whether we've sent it an ACK or a NAC. And when it says ACK has been returned, I think it means been returned to the slave from us. Because the ACK is always sent from who's receiving the data byte. So if we get an ACK, uh, rubbing the hell out of my eye. It's super itchy. Moment, yay, allergies. Allergies are great to have at this current moment in our timeline. I think we can handle master receive data ACK and master receive data NAC. Why is YouTube telling me my audio streams? My audio been getting messed up? Why is YouTube telling me my audio streams? My audio been getting messed up? No, sounds great. No, sounds great. I am not liking streaming to YouTube at all. Twitch has definitely got this set up much better. Alright. So yeah, so if we've sent an ACK back, we're not sending a start or stop. At this point, we need to send a start or stop, or both. We're not going to support queuing up writes and reads, so in this library, we won't worry about this case where we can stop and start at the same time to maintain control of the bus. But we're basically always going to stop in the not ACK case. So in the NAC, we're just going to stop. Groovy. Easy peasy. In the data ACK, we're going to write out the next set of data. So send data. Easy. That should be it. So we're gonna make I'm gonna take my LCD to include I2C. I2C dot init master. Do a nice slow bit rate to start with. Need a complete callback. Void underscore T. And we're going to do this little toggle the LED at a 1 second period. Other thing we're going to do is always see if not I2C. We're going to request. So that means we're going to need a This is going to be, what is the BNO? Data sheet. Data sheet. Register descriptions. There we go. They're listed in backwards order. Okay, so chip ID, accelerometer ID, mag ID, gyro ID. So we can read out these four, and we should get this sequence of bytes. And we're also going to write these bytes out to our LCD display we've got sitting right here, and we'll see how that goes. So we're going to do for I2C.read n. So what is this guy's address? It's 0 by 28. The register is 0. And we've got so once we call into this, busy should return true. We're gonna want another Boolean. False. Right, LCD. If so let's first check if right LCD, that this will become an else if, and then there is no else case. So if right LCD, we're going to do printf. Now, what did I miss? Got some debug code in here that's got some printfs. Could do our hex stuff. Iterate over this. And we're going to do buff I. Now this parallax LCD. That should probably be easier for me to look that up in the LabVIEW code. It has a public data type with the special characters, form feed, 12. So we're going to send a character 12 first. I need to move these get care and put cares definitions into header file. Or AVR libc C to standard out. I should be able to just say put care 12 before that. Put care 12. Hey, I found that. Cool. Okay, so the way this program works is we first init, so we're going to init serial, and 9600 baud is what I've got this LCD set to, because that's also the baud the GPS is set to, and these will be, the LCD will be using a TX line from the Pi, while the GPS will be using the RX line. So we're going to stick with this little rate. Then we initialize the I2C device as a master at 100 kilohertz. Give it this callback. We're going to need to know, we're going to need a complete this complete method. This VI. Yeah. Oh gosh, I've been spending too much time in Labuland. Void AVR. We're gonna do the master callback. Yes. Which now at this point makes this complete method seem completely unnecessary. So so in our handler here, master receive, we're gonna do the stop, and we're gonna master callback. Yes. Our callback, we can do write cd equals status I squared c. So this will then trigger us writing out the 4 bytes of this buffer. We should then see as A0 FB 32 0F. And if that happens, I might poo myself. Okay. Thread still written bad, so we're gonna change that to AVR. LCD undefined reference. Now this builds AVR I2C. Aha. AVR I2C. Okay, everything built. We got an LCD test, so make up. Well, we are not getting any data back. From that, we are getting the hello world. Right at the beginning, it prints hello world. That's happening. We want to here we go. Debug. So if we make the debug target, it adds a debug fine for the compilation. So what we can do is in our I2C code, we actually already got some of that. And then we're going to do a receive. So we probably shouldn't be doing some of this in this interrupt handler. That's all right. We're going to do a number. F. Let's see. How do we want to do this for an interrupt? It keeps telling me my audio is dropping out. Interrupt, repeat. Callback. Debug. What do I want to do for arbitration lost? Let's do the percent sign. This is going back. We're not doing any of the slave stuff yet, so. Bug. Oh, right. Percent sign is a special character. So let's not do that. Let's do ampersand. Alright, so we got an int start, transmit slave ack. So the IMU is acking us, and then we're getting a repeated start. We're getting 2 repeated starts. Starting in here, we're seeing this guy. Now, I don't know how we're getting from this to the repeated start, because next, not the start field? I don't think the start field gets cleared automatically. So in our start, let's change our start a little bit. I'm going to change our start, next and stop. Us doing these or equals, we're just going to do. Oh, I was oring it. We're just going to. So we're going to add in enabling the 2-wire bus and enabling the interrupt for the 2-wire bus. And so this way, instead of, if start is already set here, we're not going to be adding to what's already set. We're going to be setting the things we explicitly need. It's going to be more verbose with. This is actually how the datasheet specifies doing it, which probably means that they knew that it wasn't going to, that some of those flags wouldn't get reset. super explicit in specifying that. Alright, so let's make 00 B0 00 AF. Holy crap. Okay, so the next bits are overwriting what initially gets set. So let's want to see the sequence of interrupts that gets called. So we got a IR, IRSA, DA. I should really be hooking this up to a serial monitor and getting more than we need to shorten up these codes to 2 characters each somehow. Taking up too much room on this LCD display. Start. Repeat. This is going to be lowercase is a knack. Yes, so oh, this is weird. Not have it. Oh. Uploaded the file that it already had. save this. Weird. Okay, so now we're seeing start, transmit slave address with an ACK, transmit data with an ACK, repeated start, receive slave ACK, receive data ACK, receive data ACK, receive data ACK, receive data NACK, but no stop. I don't think I put one in the stuff. Oh, because we don't get a So if we compile this with debug, we get the I2C interrupt states. Compile it not with debug. We should get the actual bytes that are sent. We're getting a 00. B000AF. That ain't right. None of that is right. So for debug, let's add in what we're actually reading. 0, read B0, read 0, 0. Alright, well, getting there. We're definitely getting I2C bus operations. We're doing some stuff with the interrupt handler. I'm probably not doing stuff right with my buffers to make sure we're capturing the values properly. But I'm going to give myself a little listen to this stream here right quick. Yeah, that still sounds good. So yeah, we'll probably be streaming on the YouTubes again sometime this week. Doing some more I2C development. There is somebody I'm talking to on Reddit about some LabVIEW enhancements that they're interested in to make their lives much easier. Maybe we'll get to that at some point this week on YouTube. We'll catch you all later.